We have proved Roth theorem's theorem regarding the 6-3 problem, showing that if you have a hypergraph which is locally sparse, meaning that whenever you take 6 vertices, they contain less than 3 edges, then this hypergraph must have a subquadratically many edges. And now we see one application of this in number theory. In number theory, one of the objects that people are interested in are arithmetic progression. So we simply write AP, arithmetic progression, and then we denote the length as a number in front of it. So KAP means that it's a arithmetic progression of length K. For example, if you say 3, 7, 11, 15, then that's 4AP. One of the Roth theorem says that if you have many numbers on the integer set, then you must have a arithmetic progression of length 3. For positive epsilon, there exists n0 such that if n is large enough, the following holds. For all n at least n0. So what? If A is subset of the first n integer, and then it has at least epsilon n numbers, then A contains a 3-term arithmetic progression. And later this was further generalized by Temory's theorem, which does not just fix this length by 3 for arbitrary k. I mean, the same statement holds. If you have a n subset, density positive subset of the first n integer, then you must have a arithmetic progression of arbitrary length k. And yeah, so this kind of direction was further considered. For example, Green-Tau theorem, Ben-Green and Terence Tau proved that the set of all prime numbers also contains arithmetic progression of arbitrary length. So for whatever k you take, I mean, you can find the arithmetic progression there in prime numbers. Sorry, I was just checking whether my mic was actually working. So let's prove this using the Roth theorem. So suppose that if A is a set which does not contain 3AP, then what we do is we consider H a hypergraph. This is a 3-partite 3-uniform hypergraph with the vertex set being V1 union with V2 union with V3, and V1 consists of the numbers from 1 to n. V2 is numbers from 2 to n and 1 to 2n. V3 is from numbers from 1 to 3n. These are 3 pairwise disjoint copies of number. So you have n vertices and 2n vertices and 3n vertices, and you name them like 1, 2, 3, 1, 2, 3 to 2n to n, 1, 2, 3 to 3n. So even though we write it this way, V1 is not a subset of V2. They are disjoint vertexes. And how do we put the edges in this three-part type 3 graph? You put edges between x plus a, x plus 2a, or every x and a in the set capital A. Then what? And assume that this a has at least epsilon n number. Then h has how many edges? Fixing this, there are n choices. Fixing this epsilon n choices. So at least epsilon n square edges. Then what? By Ruzha-Moradi theorem, if H contains 3 edges spanning at most 6 vertices. So that's what Ruzha-Moradi theorem was saying. I mean, for this epsilon positive, and then as if n is large enough, this must hold. Say that those are x comma x plus a comma x plus 2a, and y comma y plus b comma y plus 2b, and g comma g plus c comma g plus 2c. So those are the 3 edges. Okay, there are 9 numbers written here, but they are actually 6 vertices. So some of them are same. On the other hand, there are no zeros. So these 3 are different, these 3 are different, these 3 are different. And then we see whether which ones are same here, which one are same here, which one are same here. So you have these 3. If all of them are different, then what happens? If you know this and this, then it automatically determines what this vertex is, right? So if you have 3 vertices here, and here there are 6 vertices, so the other 3 come from here. So there must be, I mean, these are 3 these different vertices. And if, say, all 3 are the same here, even if all 3 are same here, you have 3 vertices, 1, and then these 2 determine the third one, these 2 determine the third one, these 2 determine the third one, then you get 7 vertices, so which is too large. And even if instead of all same, say 2 of them are same and 1 of them are different, then again, let's make sure that these 2 are different, and this is another one, and you get the too many, I mean, distinct vertices. Using this kind of logic, you can see that these 3 one actually give us 2 vertices. So 2 of them are same and 1 is different. And these also give the 2 vertices. These also give the 2 vertices. So as 2 vertices in an edge determines the third vertex. Each of 3 sets x, y, g, x plus a, y plus b, g plus c, and x plus 2a, y plus 2b, g plus 2c must have size 2. So without loss of generality, assume that the x and y are same, and then g is different. Then what? Then, in order to make sure that these 2 are different edges, a and b must be same. So x plus a, y plus b must be different. And x plus 2a, y plus 2b must be different. Okay, again, there are 2 choices. G plus C should be equal to either this one or that one. Let's just assume that this Y plus B is equal to G plus C. In that case, these are same. That means that and G plus 2C must be different. So this must be same. 2C, sorry. Then what do we have? Then C is same as G plus 2C minus G plus C, which is same as X plus 2A minus Y plus B. But what do we know? X and Y are same. So this is 2A minus B. That means 2A equal B plus C, meaning that the B, A, C forms arithmetic progression of length 3, which is a contradiction. So this shows that this Roth theorem regarding the arithmetic progression in number theory can be deduced from this X3 theorem. And here it showed that if you have a subset, so 3AP free subset, then it must have a sublinear size. And that's an upper bound. So this provides an upper bound on 3AP free subset of bracket N. And what about lower bound? So this does not use the regularity lemma, but it's a interesting question. And essentially the best bound we know is by Behrend. Using, he constructed the following. He constructed the 3AP free subset with many elements and proved this following theorem. So there is the constant C such that for any, say, positive integer n, there exists 3AP free subset A of this first n integer, which contains at least n times e to the negative c square root of log n. So this is a function goes to 0, but it's going to 0, but it's much slower than this number. So this number is bigger than this polynomial. 1 over polynomial. But on the other hand, this is much faster than the logarithmic growth. So how do we do it? With some foresight, let's take the following number. Let m be the half times e to the square root of log n, and then d be the square root of log n. And we take the floors to make them integer. And how do we do it? The idea for this construction is the following. So if you have a sphere and you consider the lattice point on sphere, the points whose coordinates are all integer, then there, if you have a 3AP, then they all lie on a line. If you have arithmetic progression, so when I say arithmetic progression on the points, it's like x, y, g, and x plus a, y plus b, g plus c, and x plus 2a, y plus 2b, g plus 2c. So this are arithmetic progression. You start somewhere at a point, and then you add a vector or this point, tuple. So that's same as a line, but we know that the sphere and line, they intersect at most 2 points. So sphere does not contain any 3-term arithmetic progression. But of course, this is not a subset of n. So we kind of project it into integer. And while you're projecting it, you make sure that you don't create a new 3AP, then you get the subset that we want to consider. So what we do? We partition the lattice point, say m to the d. So d tuple, and its number is between 1 and m, is into spheres x1 to xdm square, where what's xi? Xi is the set of all points with lie in a sphere with a given radius. Then this partitions this lattice point into here, and what? By pigeonhole principle, one of them must contain many points. There exists k such that extra k contains at least m to the d divided by d m square. And as this is here, this contains no 3-term arithmetic, no 3-term arithmetic progression. Okay, and we consider this map pi and map xk to integers in first n integer. And how do you send it? We treat this as a, 2m order expression, the digits of a 2m order expression, meaning that you take xi, then you take this number. So just like when you write the number 752 is 7 times 100 plus 5 times 10 plus 2, the 10 square. You do it with this 2m playing the role of this, then you write xi. So this is written in xd minus 1 dot dot x1 in 2m order expression. So you write this way. Then what? This is injective, and this pi is injective, so that the pi x has the same size as x k. Moreover, for x, y, g in m to the d, if you have x plus g equal to y, then that's if and only if its image satisfy the same thing. So why? Because of this 2m, every xi is between 0 and m. Even if you add two of them, it doesn't wrap around. So this is between 1 and 2m, 1 and m. If you add two together, then it doesn't wrap around and then go up by 1. Okay. Yeah, maybe. Yeah, maybe you write it as 2m plus 1 here, so that it doesn't wrap around. and then carry one digit to up. So you can check that this holds. That means because xk is 3AP free, this is also a 3AP free. This does not contain any arithmetic progression. And its size is what? M to the D over D to the, D times M squared. And what's M with our choice? M to the D gives what? This is 2 to the square root of log n over e to the log n times square root of log n times M squared. It's like e to the 2 square root of log n, which is n divided by, these are like at most e to the some constant times square root of log n. So that's as desired. So this provides a lower bound. And then the natural question is what is the right number? What's the kind number for, what's the maximum size of this 3AP free graph? Recently, Tele and Mecca in 2023 improved the upper bound so that the AP free graph must have a size and most this. So, Behrend's construction says that it's at least n times e to the negative c times log n to the half, and then here with the 11. So there are still some gap, but this was a breakthrough that's showing that this kind of expression is tight. Okay, and so that was one application of this 6-3 theorem. And 6-3 theorem was proved using removal lemma. So we have seen that this removal lemma can be indeed useful. And in next video, we will talk a bit more about this Brown-Ellis-George conjecture then. Okay, then I will see you in the next video.